In this short video, we'll be looking at how we can relate reaction rate and temperature. So we've looked at rate equations and how concentration of reactants can affect temperature. But we're going to look numerically, we're going to look quantitatively at how reaction rate is affected by temperature. Now the learning objectives for this section are, can you perform calculations using something called the Arrhenius equation? You're going to be again applying a little bit of maths to rearrange this equation here and use experimental data to find the activation enthalpy of a reaction. From AS Chemistry, you learnt qualitatively how temperature affected the rate. So we looked at the distribution patterns for molecules in the same sample of molecules at different temperatures. And we found that as the temperature increased, the energy distribution of the molecules changes. So at higher temperatures, if we look at this point here, remember EA is the minimum energy needed for a reaction for collisions in a reaction to be successful. And as the temperature increases, the profile is such that there is a significant increase in the number of molecules who have energy greater than EA. So we're going to see how this activation energy is related to the rate constant in our rate expression. So now let's start to put some values into what we've known from GCSE is this term activation energy. And this was derived by somebody called Arrhenius in this Arrhenius equation. K is the rate constant that we met in the previous video. So when we looked, for example, at the reaction with propanone iodine under acidic conditions, the rate constant or velocity constant is this lowercase species here, and that is the rate constant. And we found we could assign values to that at a particular temperature. So K is the rate constant from the rate equation. A is something called the pre-exponential factor. And this is related to the number of collisions between reactant molecules. And we know from GCSE that if you increase the temperature, the number of collisions between reactant molecules, the frequency of these collisions increases. So we can now give this a value. And finally, this term here, which is the exponential factor, so A is the pre-exponential factor, so E to the power of the activation energy here, R is the gas constant, and T is the temperature in Kelvin. So let's see if we can simplify this expression. So let's just go through those again. K is the rate constant or velocity constant from the rate equation. A is something called a pre-exponential factor because it goes before E, the exponential factor. And E is raised to the power EA divided by RT. So let's simplify this. If you feel that you're scared of maths, please do not be overwhelmed by this section, because all you're going to have to do is to take data that you're given and plot it in a graph. But for now, let's just look at how we've taken the Arrhenius equation here and converted it into this more simplified form here. I'm going to make life a whole lot easier. We're going to convert this, what looks like a complicated equation, into a graphical format. So we're going to take logs of both sides. So we're going to we take log of this, that now becomes natural log of K. If we take the natural log of A, which is here, the pre-exponential constant, and if we now take the log of this here, and we can bring it down, it becomes minus EA to the RT. Or natural log of the rate constant equals minus EA over R times 1 over T plus ln A. And this then turns itself into a beautiful Y equals mx plus C equation. So let's look at some typical data that you would be given if you are varying the temperature for a chemical reaction. So in this experiment, some hydrogen iodide was taken, and when heated it decomposes into iodine and hydrogen gas. So experimentally, the rate constant, as we looked at in the last video, was determined, and here are the different temperatures in Kelvin at which the experiment was carried out. At this point, you will need to get yourself a calculator. So could you pause the video at this point? Once you've got your calculator, what I would like you to do is, on your calculator, could you do 1 over these temperatures in Kelvin? So all you need to do is divide 1 by 633, and that goes into the table here to give you 1 over T in Kelvin. At this point here also, on your calculator, you need to find the natural log function, ln K. And what I would like you to do is practice putting in the numbers for this value, 1.78 times 10 to the minus 5, and finding its natural log. Could you do this for each of these values? Pause the video whilst you do it and check your answers. It's really important that you're able to do this on your calculator. So you need to find the natural log button, input this data, and then write your answer out. You can then unpause the video and I'll reveal the answers that you should get. So first of all, for 1 over the temperatures, notice here it says times 10 to the minus 3. So on your calculator, that might come out as 1.579 times 10 to the minus 3. So instead of writing times 10 to the minus 3 at the top for each of them, we've put that as 10 to the minus 3 at the top. So the units will be Kelvin to the minus 1. Can you now find the values for the natural logs of these figures here? There are no units for logarithms, so there are no units here for logarithms. So can you go to the natural log function on your calculator, and then I will reveal the answers. So if you pause the video, carry that out this on your calculator, and then I'll now reveal the answers. So these should all be negative numbers, because the actual numbers were 10 to the minus 2 here, so you can see that it's got a negative sign. So these are all negative numbers. Notice we've recorded them to 3 decimal places. They've all been recorded to 3 decimal places. What we're now going to do with this data is to plot a graph. And I'll walk through the graph plotting with you if it's likely that you haven't got graph paper at home. So now let's look at the graph that you would plot with this data. So let's revisit the Arrhenius equation again in the natural log form. Ln A is going to be the y-axis. So the data that's going to be on the y-axis is this column here. The data that's going to be on the x-axis is this here. This is the x-axis, 1 over temperature. So this forms our x, or our horizontal axis, and y, the dependent variable, the natural log of the rate constant, is dependent on the temperature, so that goes on the y-axis, on the vertical axis. So our graph, if we sketch this out, the x-axis is here going along the horizontal axis, and because our y-axis all has negative values, one of the most common mistakes make is for students to take this as the highest value. It's not, it's the smallest value. And notice that ln K doesn't start at 0. So there is no reason why your y-axis should start at 0, because otherwise you're going to end up with all of your data scrunched up into one very small portion of the graph like this. So we start to plot the y-axis with -4 here going all the way down to -11, because it runs from -4 up to almost -11. So make sure that ln k, your y-axis, goes even more negative as you go down. One of the most common mistakes is for students to use the positive values. So notice it's becoming more negative as you go down. Notice here that these values are all 1/t, but you must write on here times 10 to the -3. And that way it makes it a lot easier to plot this data. So from now look at our graph that results, we have a negative gradient. So the x-axis here is 1/t times 10 to the -3. The y-axis is natural log of k. Notice there are no units. And the gradient should always be a negative gradient. If your gradient's going that way, positive, the probable reason is you've got this axis upside down, so it should be getting more and more negative. Right, so let's look at our equation again here. This is the y-axis, and therefore if this is the x-axis, minus E over AR minus E, the activation energy, over R is equal to the gradient. And therefore if we can get the gradient, we can rearrange this equation, because we know that R equals 8.31 joules per Kelvin per mole, because that's the gas constant. We can work out the value of negative EA, and therefore we can find the value of the activation energy. So a quick recap of how you do gradients again. You get the tangent, in this case it's a straight line so it's easy, of the gradient, and what we've done here is taken this value here and this value here, which is approximately 6 take away, which is about 2, divided by the y-axis, which is roughly 0.1 times 10 to the -3. So here we can see that the gradient is ln k, which is the y-axis, divided by the 1/temperature, and the units, incredibly, come out to Kelvin. That is the gradient, because if this has no units and that's 1/k, then the units of the gradient are in Kelvin. So how can we now use that to find our value of the activation energy? First of all, if we take both sides and times them by -1, that gets rid of this negative sign here. So here's -1 times the gradient times by R, which is the gas constant. So the activation energy is plus 23000 times by 8.31, which is the gas constant. So our activation energy is going to come out in joules. So if we divide the answer by 1000 or times it by 10 to the 3, that will give us our activation energy in kilojoules, and it should always be a positive value. Activation energies are always endothermic. Energy needs to be put in. So it's always going to have a positive value. If you're coming out with a negative value, you know you've got your gradient upside down. So let's just go through that calculation again. The gradient, when you plot your graph of 1/t here against natural log of k here, is minus activation energy over the gas constant. Rearrange this equation, so EA equals gradient times the gas constant. The gradient was minus 23,000 Kelvin times by your gas constant, which is 8.3 joules per Kelvin per mole. So notice that Kelvin cancels out, and therefore the activation energy comes out as joules per mole. If we divide this by 1000, the activation energy for this particular reaction is plus 190 kilojoules per mole, and that is to two significant figures. So from AS we all recognise this Maxwell-Boltzmann distribution again, but now we can have a value for the fraction of molecules using the Arrhenius equation. So remember the original Arrhenius equation relating the rate constant here to the temperature and the activation energy. So say for example in a typical laboratory that's about 300K or about 25 degrees Celsius, and we know that the fraction of molecules with energy greater than 50 kilojoules per mole, that's the activation energy, is going to substitute into this equation here. So remember that this factor here is the fraction of molecules with energy greater than the activation energy. So here is the EA, there is the gas constant, and there is the temperature in Kelvin. So if we work this bit out in our calculators, it comes to minus 20.8. Now if you do that onto your calculators, this tells us that 19 times 10 to the minus 10 are the fraction of molecules that can have successful collisions. What does that actually mean? It means that only 19 molecules in every 10 to the power 10 molecules have enough energy to react. So that's a tiny fraction of molecules. 19 molecules in every 10 to the power 10 molecules have the energy to react. Now let's just warm the lab up a little bit. Let's increase it by a mere 10 Kelvin. So again, if we substitute that into this equation here, which you can easily do on your calculators, you'll notice now that that drops down to minus 19.43. And get rid of the exponential factor here on your calculators, that now comes out to 36 over 10 to the power 10 molecules. You can see that the fraction of molecules has almost doubled by increasing the temperature by 10 Kelvin. So that's where the biology thing comes. If you increase the temperature by 10, the reaction rate tends to double. And that is because you've effectively doubled the number of molecules that can have successful collisions.